All right, hello and welcome back to the Lightning Talks. Thanks to everyone who joined us yesterday for 2 hours of interesting talks covering everything from publishing a new book on the geology of Africa to machine learning and the various steps in between. Really pleased to bring you a second day of talks. Again, the talks will be 5 minutes with a 5 minute kind of handover between them. Just bear with me. And our first speaker today comes from Edinburgh, Sean, who is ready and waiting to go. So without further ado, I will hand over to him and we'll catch up with you all in 5 minutes.
Cool. Well, thanks a lot, Dan, and excited to get started. Yeah, so just I'm going to give my talk in this Jupyter notebook, which is something that's new for me, so we'll see how it goes. So just quickly, who I am and what I do. My name is Sean Walker. I'm a consulting geophysicist based in Edinburgh, and I work primarily in the mining industry. And what that entails is generally doing QC processing and version interpretation of pretty much any data my clients want me to look at, which is usually EM and potential fields. So I've been involved with the software underground since probably about 2018. I went to the hackathon in Copenhagen and it was great, had some great beer and good fun there. And since then, it's mainly been lurking on Slack, but I'm trying to do more, like today, giving a lightning talk. So do I use Python or any of this stuff in my day job? Not really. I'd like to use more. It just seems like every 2 years, I typically attend a conference or a workshop and I get excited and nothing really comes of it. And I was kind of hoping that this week would be able to do a little bit more than that. So until yesterday, I really wasn't sure what else I was going to talk about, but then I saw Joe's Kington's amazing image processing tutorial, and there was just lots of really neat things in there that I could see applications in my work. And unlike what I've done in the past, which is write something down in a notebook and then go home and forget about it, I was already home. So I just thought, hey, let's try and give it a go. So I'm going to focus particularly on his lineaments and image segmentation bits. So essentially, since late last night, I think the tutorial finished at 10 my time. So last night and this morning, I did a little mini hackathon. So I had to first find an area to work. Sudbury is a good place. It's based in Canada, big nickel deposits. It's a big nickel there also, if you've ever been there. Um, but there's lots of data available, freely available from the government. So if you don't know what Sudbury is, if there's a lot of oil people here, maybe don't know what it is. It's a massive impact crater. It has lots of nickel deposits. All these little red dots all around the outside of this impact crater structure are deposits, and this is a cross section, and essentially the nickel's kind of on that contact there. So anyways, it's a great place because there's lots of data that you can grab. So I did that. So without further ado, I'm going to see if I can do what some of Joe, replicate what Joe did on some of my own data. So I'm not going to click through this. I've already run this. Basically, it's just loading. So I'm going to show what I have. So this is just another view of the geology. It's pretty shoddy looking TIFF, but essentially you get the idea of the impact structure. So I also grabbed some satellite imagery. You can kind of see a little bit of a hint of what's going on there. In grayscale, it's not great. But if you look at a DEM in grayscale, then things start popping up. You can actually see there's quite a bit of structure. This is in I guess the Canadian Shield, so there's quite a bit of exposure and outcrop and lots of fracturing in the crystalline rocks there. So a nice thing that outcrop gives you is radiometric data. So this is a ternary plot of the airborne radiometric survey over the area, and you can kind of see, without going into even what all the colors mean, that we're mapping changes in lithology and yeah, so there's a lot of detail, and you can even kind of see the shape of the impact structure as well. So I'm going to try two things. So the first is start with a lineament analysis. Oh, I've only got 1 minute left. So basically, I'll try. Is that better? Okay, so I'm running out of time. So basically I did two things. So tried to skeletonize my DEM, and I tried with two different variables. Basically you get a bunch of squiggles, but squiggles are great, but they're not that great. So Joe showed us another thing using a Huff transform to try and actually do something with your skeletonized squiggles. So you actually fit lines. And then the nice thing with lines is, so we've got, a bunch of lines, but now that they're lines, we can actually get information out, so we can see that, there's actually directions. So this can kind of then, do something quantitative. And then just before I run out of time completely, I just tried to segment this image. So it's a ternary plot. So there's 3 elements: red, blue, and green. That's me at a time. Anyway, so the segmentation, I'm not going to go into it because I don't understand it, but essentially you can get something like that or something like that. And then with that, you can actually, pull the bits of data out and do something quantitative. So anyways, I was pretty excited that I actually managed to do that this morning. So this is huge thanks to Joe and Swung and Transform.
Really, really nice stuff. I always love to see something done in the community reproduced. This is something I always try to do. So how long did it take you? Did you get enough sleep
Yeah,
after this
no,
mini hackathon? Or
yeah, no, I kind of got all the data last night. The bulk of it was just trying to get it registered and get it into Python. I mean, that's the biggest struggle I have. I mean, I had a lot more data that I wanted to play with. I had some mag data and I was going to do some cool stuff, but still just getting it in and then getting it registered. I mean, you can see it's all in pixels, so I don't even really have it registered. It's just all from the same area.
so if anyone would like to help troubleshoot these problems over the weekend or ongoing, I think again Joe's tutorial is up on the YouTube channel. If you missed it yesterday, it's a really great tutorial. Image processing in Python. It blows my mind that we can do it now. I can remember coloring things in and sticking things together only 5 or 6 years ago.
Yeah, I mean, that's the thing. Like, the thing that took me time was just getting this data in. It's just this. It's one line of code to make this
Yeah.
picture. Basic. It's amazing.
So
It's mind.
there's a bounty for anyone making an effective data loader to speed up this geophysical image processing.
Oh, I'm sure they're out there. I just don't know where they are.
Yeah. Well, if anyone does, drop it in the Lightning Talks
Yeah, that would
channel,
be great.
because I would like to know as well. But thanks so much for showing us your little personal hack. It's the kind of things I love to see.
Cheers.
Um,
Thanks.
and yeah, have a great rest of the day.
Yep, you too.
All right. Returning from yesterday is Matteo next, who I've really got to know this hackathon through these talks and collaborating. His talk yesterday is available on the stream. It's the second one, which is some very interesting image processing again, using different color maps and different processes to show things. So yeah, going to bring him in and get set up for the next talk beginning at 10 past the hour. So if you'd like to get a drink or get up, you've got a couple of minutes to stretch your legs. Yeah. Hello, Matteo. How are you today? Hmm? You there? All right. I'll have to vamp for a couple minutes. So if you are inspired by these lightning talks and you have something you want to share, I mean, get on organizing it. I think the feedback has been that we need to do more of these. So it's a real opportunity to share whatever you're passionate about or hacking on at the moment with everyone. And yeah, I mean, for me, it's been great. I haven't seen any of these talks in advance. I know some of the speakers well, some not so well. So
Hey,
it's
Dan.
hey, Matteo, great.
I'm sorry.
It's no worries. I probably should have asked you if you were ready to go live beforehand. But yeah, just to finish up, it's a really good way to connect with people, ideas, and get into this world of reproducible ideas and code. So, Matteo, are you ready to go for a second day?
I am, yes.
Fantastic. I will leave you to it for 5 minutes then.
Okay. Morning, welcome everyone. Thanks for attending. The title of my talk is Be a Geoscience Detective. And here's the repo. My objective is to show a method to rigorously validate or challenge otherwise claims about geophysical inversion results in papers.
So, are you sharing your screen, Matteo? Or are you presenting without a screen?
Oh, that's great. Give me 1 second.
Yeah, no worries. There we go. Perfect.
So the objective is show a method to validate or challenge claims about inversion results published in papers. It's my take on data geoscience meets repro zoo. So here's a figure from a paper in the CSCG Recorder on inversion DRAM processing. And I actually quite like this paper, but this is the extent of how an inversion result is proved. And so I'll explain. I have on the top row a method without extra processing, and on the bottom row, 2 plots for an inversion with signal protected noise attenuation. The left is a colored impedance section with spliced in a blind well impedance log and color to match, and it looks okay. And on the right side, in both cases, the inversion well result versus the well log. And the extent of the evaluation is that the data with the extra processing shows a better fit to the well. That's it. There is no score, no square, nothing to actually validate that one method is better than the other. So what I did is I hand digitized the logs, the inversion traces from the figure, the horizon, and then I split everything in an upper lower zone because I wanted to evaluate in 2 different zones, and I added an arbitrary geologic top, and I used an error flag function that I wrote, which I'm not showing, but essentially this is what it does. It calculates the difference between the log and the inversion result at every sample. Then it calculates the median difference and the median absolute deviation for all those differences. And then for every sample that has a difference between log and inversion that is farther from the median difference than 0.5, I trigger a prediction error flag. And this is more robust than using the mean and the standard deviation because it's more robust towards outliers. So here's the result. On the right side, the inversion with the extra processing, and on the left without. And I would argue that yes, if I use this as a reference, this fake top, where I see an increase in impedance, the upper zone, I see less flagged samples in red with the extra processing, but in the bottom zone, I will argue no. And you can do things with pandas like sum up, count the percentage of samples that have been flagged for each result, and that matches the visual intuition, because in the upper zone for the with extra processing, I have 35% against 48. So yes, better. There's less samples that are flagged, but at the bottom, similarly, a lot more, 73 against 54. And I decided to dig a little deeper still. So how can we be confident about those 2 betters that I mentioned? And the answer can be given with a bootstrap confidence interval for the proportions of flagged samples. And in the next 2 plots, which I created with this data science library, I show the result of 20,000 bootstrap samples for the errors in each of the 2 methods for the 2 zones separately. And this is the upper zone. I have in yellow the distribution of all the bootstrap samples for the method with the extra processing, and in blue without. and there's the distribution, and then the little lines are the confidence interval. So there is quite a bit of overlap. And this is the lower zone, similarly, distribution and confidence intervals, but with a bit less overlap. So I would say, based on these two plots, that I am more comfortable with the conclusion for the lower zone, which was that the method without extra processing had overall less percentage of error between 0.4 and 0.60 something. And that's it. I'll leave you with a quote from Sergey's 52 Things You Compute in chapter, which you can read. I think I'm up. And read this paper. It's really worth the while.
Yeah. Thanks. Great to see some more in this area of being geoscience detectives. I think it's an important thing to bear in mind. How is the 52 things coming together? Have we obviously we've been editing it. Are you happy with the progress? Is there more to do?
Yes, I think I have 4 or 5 papers that I'm hoping in the next couple of days to tackle. The week has been slow, but I expected that. We did really good. We had good progress on the weekend. There's a couple of people that maybe will add on with at least one paper, so I'm really excited, and I hope we'll keep the momentum after the transform.
It's been really fun to read these papers in progress. I'm not an academic reviewer by any means, but they're really punchy blog articles. There's some really cool stories from across Swung is how I'd really categorize it. You got a minute or two if you want to add anything else, or give a plug.
Well, about this talk, I if you don't mind, I want to take you this with a grain of salt. I've made some interpretations choices, so I've added horizon. I have chosen a specific statistical measure to do this comparison, and perhaps even some hand digitizing mistakes, which is to be expected. But I'm very pleased with this because it shows a way of thinking and a methodology for tackling some of these claims that are made in some of these papers about, this method is better than this other. It's so common to see that kind of comment and nothing quantitative to back it up.
Yeah, I 100% agree. And the actual visuals you made are so nice and clear. I think that's a really, really strong plot. Well, thanks for volunteering today and yesterday were 2 great talks.
Thank you.
All your contributions to the hackathon. I'm going to let you get on with your day and bring in our next speaker. A man I know quite well, having spent some time with him at several hackathons. He's very fond of cheese, among other things, including Python. So we'll bring in Alex, who joins us from, I think he's in Germany at the moment. And I'm not entirely sure what he'll be talking about. How are you, Alex?
Hello.
Are you doing well today? You having a good transform?
So far, yeah, really interesting talks and tutorials. So that was awesome. Not so productive on my PhD this week, but
yeah, great. And how long? I'm going to ask you, how long have you been associated with the Software Underground?
I think I joined when I started my PhD, which was like a little bit more than 2 years ago. Yeah, and then went to hackathons. And
yeah. And how are you having enough cheese and wine this year?
Yeah, I'm really lacking on that regard.
Cool.
Like no cheese.
Cool. Cool. So have you been hacking at all, or have you been purely talks and tutorials this week?
Mostly talks and tutorials. I hacked a bit on like the GenPy chapter for the 52 things in geocomputing. Yeah. Basically brought that up to like the current version of GenPy, because it changed a lot in like a year.
Yeah.
Yeah.
Great. So what are you bringing us live for 5 minutes then? What's changed your life in 5 minutes then?
Well, let's see. Let me share my screen. That should. Can you all see that?
Yep. Perfect. And I will hand it over to you and be back at the end.
Awesome. Yeah, so I want to talk to you about how to learn uncertain structural geomodels on topology graphs, which has been a bit of a research I've been doing during my PhD. So first of all, what is geomodel topology? And here we have a little simple 2D layer cake model. And you can see that each layer here is represented by a node in this graph, and each stratigraphic connection, each layer interface is shown as an edge in the graph. And this is basically what we then call a topology graph. If we move then to a more complex model here, angular unconformity, you can see how the geomodel topology changes and incorporates all the tectonic and stratigraphic information in here. If you increase complexity, of course, the complexity of your topology graph increases. So basically, topology encodes stratigraphic and tectonic relationships in geomodels into like adjacency graphs. And we want to have the idea to use that to like constrain stochastic geomodels. But first of all, like how do we simulate geomodel uncertainties? Like the simplest way I can think of is we start with an initial geomodel, a ground truth. Then we add some stochastic parameterization. So basically, we make a probabilistic description of our input data using probability distribution. So instead of single points, we basically get describe it as a distribution from which we can sample. And this is basically called Monte Carlo uncertainty propagation or Monte Carlo sampling. If we draw samples from that, create structural models out of that, and then we basically get a geomodel ensemble. Here shown as entropy slice through 2,000 geomodel samples, and we get a nice sense of the uncertainty. But of course, not only like with changing the geometry of the geomodel to simulate the uncertainty, we also get an effect on the geomodel topology. And if we like make a horrible parameterization, a stochastic parameterization, you can see that we get like unrealistic geomodels where whole layers just vanish. And you can directly see how the graph, the topology graph, changes in these models. So it would be a way to filter out unrealistic geomodels, which becomes ever more important. The more complex the geomodel is, the more difficult it is to properly make a stochastic parameterization. So what we then tried is basically using Bayesian inference to learn our probabilistic geomodel on this topology data. Here you can again see the Monte Carlo uncertainty propagation, which is 2,000 geomodels, and they in total actually contain 100 unique topologies in there, so quite a lot of diversity, and I'm sure not all of them are geologically valid. So what we then do is like we add an observation or a priori knowledge, in this case the initial topology graph. So basically we say we want to constrain this stochastic model to this initial topology state, and well, we can do that with an approximate Bayesian inference or approximate Bayesian computation. And basically what we get is a posterior geomodel ensemble that now contains, in this case, only one unique topology because we've constrained it so far. Yeah, so, and the research questions we're trying to like answer with that or look into is like, can we use these topology graphs to encode a priori knowledge about tectonics? Because implicit geomodeling allows only limited input data, like for example, in GenPy, it's the interface points and orientations. So we're missing out on a lot of geological knowledge here. So can we make use of this to learn uncertain geomodels on our additional geological models, knowledge that can be encoded maybe in these topology graphs? And last but not least, if you want to play around with GenPy, or if you've joined the tutorial on Tuesday, GenPy has a nice little topology asset, so you can just import it and compute the topology of your geomodel in like one line of code if you want to play around with that. Yeah, thanks.
Thank you, Alex. Keeping to time. You actually had an extra minute if there's anything else you wanted to add.
Oh, really? Oh, not really. Like, so, I mean, if anyone feels inspired to play around with topology, that's always awesome and can come up with more ideas than I can to actually use this for something. And well, we just submitted a paper on this research. I was hoping to be able to share the preprint already, but it's, you know, taking its fair time. So yeah, maybe later on.
Not everything can be done in a matter of minutes online. So, yeah. I mean, GenPy to me is a big transform story, because I remember you showed it off at the last transform, and everyone really took to it and started. Did you find the contributions increased after it was exposed to Swung and the progress kind of went faster, or I don't know? It felt like that was something that really benefited from us playing with.
Oh yeah, I'm sure it did. And I mean, over the last months and months, we've seen like a really drastic increase in like GitHub issues, which is certainly also bugs, but also like questions and interest, and the community really like trying to work with us more. People adopting the technology. And I think that's also due to we made it much easier to contribute with like contribution guidelines, etc. That probably helped all the GitHub stuff a bit.
Question from Steve in the chat. In GenPy, do you specify the topology graph as an input to define the model, or is that just internal representation?
That's something you extract basically from the existing geomodel, so you cannot go the other way around. Not with GenPy, no.
Okay.
I mean, for simple models, you could do it probably with NumPy, just fiddling around, filling. But you have to make a lot of assumptions, like how big is each geobody. You'd have to encode a lot of additional information to actually make it work the other way around.
Yeah. Is there anything next in the GenPy roadmap? JavaScript of GenPy? I don't know. Can you share some spoilers for the future?
There is actually a master student working on like a little web app right now to like use sketch drawing to like create geomodels and add uncertainty parameterization more intuitively. But that's a work in progress. So.
Cool. And what are you hacking on at the moment? Have you got plans for the weekend or?
Yeah, I wanna actually make or complete a little tutorial on how to take Petrel surfaces, export them, and basically create a GenPy model out of that and do a uncertainty simulation. So hopefully that will be my output.
Fantastic.
Nice notebook.
Yeah. So I would definitely look out for that, because the more I can take out of Petrel, the better.
I agree.
No, thanks so much for your time this morning, Alex. Have a great rest of the day. I'm going to bring in our next speaker. So next up, we have Leonardo, I believe. Let me just check my schedule. Yep. And we'll bring him in right now. So don't forget to check out the GenPy tutorial. Again, it was live, but it's on YouTube. So do feel free to catch up. I can vouch the GenPy guys are fantastic in the underground. I met them last year, and there's been a lot of great work on that 3D modeling package. I mean, I say over the last year, it's really good. Hopefully. Hey, good. I guess good afternoon to you. I think you're in Liverpool at the moment, or?
Yes, I am. Yeah.
Fantastic. How is it down there? How's the weather today?
You know, the usual: cloudy, rainy, windy.
All of the above. It sounds almost like Stavanger. Great. So you got a couple of minutes. If you want to introduce yourself and kind of how you came to Swung and what's going on in your part of the software underground.
Yeah, sure. So I'm Leo. I've been around since the Google group that Matt mentioned yesterday. So feels like ages now. But yeah, so really just enjoying Transform, trying to fit it into the busy week here at the end of the semester. I'm currently a lecturer at the University of Liverpool, so we're finishing the term right now, so a lot of marking to do.
Cool. All right, well, you are pretty much on time if you want to start your lightning talk, and I'll catch up with you in 5 minutes.
All right, let me share my screen. All right, so hopefully everyone can see that. So what I wanted to talk about today is a project that's very near and dear to my heart, and that's Facendo Terra. It's open source Python tools for geophysics. And there's the website link over there. I'll put it again at the end. Right, so basically what I wanted to talk about a little bit is, so first, hi, I'm Leo. We kind of got around to that already. So I work at the University of Liverpool since August last year, and I'm trying to set up the computer-oriented geoscience lab there, where we're working somewhat in the intersection of machine learning and data science and open source software in geoscience. So the Fatiando project started way back in 2010 while I was a master's student in Rio de Janeiro, because from Brazil. And I actually dug around in the commit messages, and I managed to find the first commit for Fatiando, and that was in April 30th, 2010. So keeping everything in version control is always a good idea. And you might notice that this was converted from Subversion and then converted from Subversion to Mercurial, from Mercurial to Git. So that's the third source control, revision control software that was used for Fatiando. So kind of old school. So this was the first example gallery that we had. So the project started off as a mishmash of everything that I was doing for my master's. So there was everything from simple seismic tomography to 2D gravity modeling. And you can really date the screenshot by the social media icon there for Google+, which was a great success. So fast forward a couple of years, Fatiando did turn out to be a pretty, it evolved into something that was actually kind of useful. So version 0.5 was the last one we released of this package, and it's still in use today. I use this for a lot of my research, for building some crazy weird inversion methods like this one, where the solution grows around seed prisms instead of doing the normal least square stuff. I also used it extensively for my teaching when I was in the University of Rio. So I was running through in Jupyter Notebooks, doing seismic wave simulations and things like that to teach these concepts. But turns out that a lot of the design decisions I made back then were really poorly done, and I was still learning a lot of stuff about open source development. So in 2018, we started a complete rewrite of everything. And instead of having a single package, we divided into the 5 packages that you see it now, and with more perhaps to come. So Verde is the first one we developed, and there was a tutorial on that yesterday, so I'm not going to talk too much about it. Pooch is one I'm really excited about. It's for managing downloading of sample data sets for other Python packages, and all the Fatiando packages use it. And recently, Scikit Image also released their first version with Pooch as their backend for downloading data, so that was exciting. We had a day 0 bug that was really interesting. And Harmonica is the new gravity magnetics package, and Santiago is going to talk about that after the break. So a lot of this was motivated by Santiago joining the team back in 2015. And yeah, he's really brought a breath of fresh air to the project. And he's currently one of the lead developers, I guess, for Harmonica and Rock Count. And you'll see more from him in a little while. So the main idea was to hold all these packages to a higher standard than we had before. So we've adopted a documentation first approach, where we'll write the docs first and then write the code that implements it. That lets us avoid making bad design decisions based on convenience, when instead the usability would be terrible. So we catch that kind of stuff early by doing the example first and then doing the code. So full tests, better use of semantic versioning, trying to automate everything as we can, and do code review on all our pull requests. We're also focusing a lot on really trying to build the Fatiando community and really strengthen that, try to get more people involved. So we have a dedicated Slack group, but most of us are on Software Underground as well. We have code of conduct, contributing guides, maintenance guides for how to make releases and that kind of stuff. And we recently developed authorship guidelines, and we're really trying to mentor new contributors. So I highly recommend looking at those. And if you want to steal any of that, feel free. Finally, we're doing regular community calls. We have one next Friday. If you want to join, please feel free to join and chat with us. And that's it. So I'll leave the URL and the call for the Slack group.
Great. It's really interesting to see how you're rebuilding everything from the ground up. So at what point did you just say, we're done with package 1, it's time? You know, what was the kind of final frustration that made you say it's quicker? Or
Python 3, I guess, was the major. Yeah, we've been putting off updating to Python 3 for quite a while, and I kind of got busy with life and couldn't really do much developing. But yeah, I think that was really around 2018, and I started chatting more with Santiago, and we kind of decided that it's more work maintaining that package and upgrading it than it would be to just start fresh. So yeah, it was.
Yeah, and you gave a tutorial on Verde earlier in the week, did you? Or
yeah, yesterday actually.
Yesterday, great.
Yeah.
Yeah, and obviously that's available on Catch Up for those of you who missed it. Again, it's a real good tutorial. It's really nice to see tools being built. I think is one of the things. I don't know if you found this, that we build scripts that work and projects, but actually building tools is a whole other kettle of fish.
Yes, yeah, I found that the hard way while developing all this stuff, and that's part of the reason why it was best to just scrap everything and start again with the knowledge that I kind of accrued over 8 years or so doing it. Yeah.
Yes, there's some people joking about Python 3 in the chat that was obviously the catalyst for many people. Was because for me, I wrote my first ImageNet in Python 2.7, and then it stopped working, and that then took me off using Keras, I think, into like TensorFlow and then PyTorch. So yeah, what was so different about Python 3 that just made nothing that was built before it work? I guess.
Oh, actually, upgrading to Python 3 wouldn't be much of a problem for us, actually. It's mostly strings that broke everything, and we didn't really use them too much. But it was also the ecosystem was very different back then. So when I first started, there was no Jupyter notebooks, so interactivity in a web page wasn't really a thing. There was no PyVista, so I had to roll my own VTK wrappers and stuff like that to do the plotting. And there was no X-array, so we had to sort of invent ways of handling grids. So there was a lot of this stuff that was missing. And since it exists now, it makes more sense to design new software around these new tools rather than maintain all that old crudge.
Yeah, managed decline.
Yeah.
No, it's very cool. And are you hacking this weekend, or were you hacking last weekend? You know what's.
I wanted to. So people are hacking on Fatiando related stuff on the T20 Ghostin hack project, and I think there's a new one for workflows, but I've just not had the bandwidth to really participate too much this week.
Yeah, I mean, I think you're allowed a little bit of a breather with the amount you put into Transform. But thanks for the great talk and excellent tutorial. Yeah,
thanks for hosting.
Check out the packages, everyone, and yeah, there's plenty of comments waiting for you in the chat, so I'm gonna let you go.
All right.
Thanks. Okay. Yeah, that's always been an interesting one for me. Is when do you say enough is enough? It's time to make the tool or change the workflow around entirely. And I think it's always good to have people around you using your scripts to push you to innovate. So we're running pretty nicely to schedule today. So I'm going to bring Florian in, who's our next speaker. There is about a minute if anyone wants to get a quick drink or stretch their leg or whatever. We'll be starting at 22 the hour. Hi, Florian.
Hi.
How are you today?
Good, thanks. And you?
Yeah, really good. It's been a great week so far.
Oh, yes.
Have you had any particular talks that have stood out, or tutorials or events?
Well, I participated in the GemPy tutorial, giving my short lecture on modeling as part of that, and well, a bit of contributing to the hacking last Sunday, because we have some additional work on GemPy, the link to geographic data we've been working on for quite a bit now. And we got some awesome feedback already. So really enjoying it. Far too little time because at the same time teaching, administration, everything else. So yeah. But it's good that it's all online. So actually this morning I watched the YouTube sessions from yesterday from Lightning. And I yet have to catch up on Verde because that's something which I really wanted to see. Great stuff from Leonardo that he's been doing. So yeah.
Yeah, it's a very, very innovative community. I mean, I've learned a lot from
Oh, yes.
hosting the talk. So, for the record, I don't have a list of who's speaking. I have a list of who's speaking and nothing else. So everything is brand new to me until I bring them into the meeting room.
Okay.
So with that, Florian, it's over to you for your 5 minutes of fame.
Well, okay, let's see those 5 minutes. So I need to share my screen, right? Need to go there. Can you see that now?
Yeah, we see
Okay.
your lovely kinematic model.
Okay, fantastic. Because actually, I'm not going to talk about GemPy. We have many talks about GemPy. Also a bit after me again, Alex before me, and of course our tutorial session. But I wanted to share with you a bit about some other work that we've been doing over the last years, a bit minor part of our research, but maybe still something which could be interesting. And this is kinematic modeling, actually, in our package PyNoddy. So what is kinematic modeling? I kind of mentioned that for those of you who attended the GemPy tutorial, when we ask ourselves, how can we actually generate representations of interfaces, we can think of interpolations, like actually, as we see here, picking points and then interpolating in between an interface. Or we can say that we somehow describe how things evolved over time using what is called kinematic modeling. And we can go all the way through to full process simulations, actually, simulating how mountain bells form using all the physics and all bells and whistles. And if you look at this at a bit of a bird's eye view, you could generally say that if we are, on this right-hand side over here, process simulations are incredibly difficult for actual cases, let's say, because it's very difficult. We don't know the boundary conditions, the rock properties, and so on. If we go a bit to the left here, we are more on the side of direct observations and data that we can use. And that's, of course, where things like all the geomodeling packages and geomodeling steps are, in a sense, shining. Somewhere in between is this so-called kinematic modeling, and that's what I'm going to talk about today. So the idea being that you could say you start with some idea of your initial settings. Say you had a sedimentary sequence of layers, then you fold it maybe, and you deform it along faults and so on. So you basically build up your model by defining a geological history. Only kinematically, so no dynamics involved. You do not actually simulate how the rocks deform. You prescribe the deformation fields, but it's a very efficient way or it's a good way at least to see how different potential geological events overprinted on each other. Just a note here, of course, this interpolation side, this is where, as I said, geomodeling lives. So GemPy, for those of you who attended the tutorial or know about it, this is where GemPy is situated. So what is kinematic modeling, and especially PyNoddy? So credits go back, all the credits to Noddy, and this idea behind it is all based on the work of Mark Jessel, actually in his, I think, bachelor's. So Noddy was one of probably the first geomodeling packages really ever written with a graphical user interface. PyNoddy is in a sense a front end for it. It still uses Noddy under the hood, but making it accessible through Python, just a bit more flexibility. So what does it look like? You can think of, let's say, start with an initial stratigraphy, and then let's say you prescribe a fault. So you can see here now, we are offsetting basically this fault block on the right hand. The hanging wall is here shifted downwards. We can say we also do this maybe for another fault. So let's say we look at another event here on the right hand side. And so far, this is all simple, but where it gets complicated is when you say, let's now see what happens if we combine both events. So we have fault 1, we have fault 2, and they intersect and affect each other in order to give us this a lot more complex picture. And if you look at this, I mean, for anyone who is kind of, in structural geology, has a training in structural geology, this is easy to see. But for many other people, it's not quite easy to understand how actually multiple, let's say, offsetting events will affect each other. And that's possible with PyNoddy to simulate. What we also have built in PyNoddy and in the original Noddy code as well is gravity forward modeling and magnetics. So you can also directly calculate the output of one of these kinematic models. And that's nice because you can say, okay, let's just change something in the model. That's very easily done also in Jupyter notebooks if you like this type of interaction. And you can look at the difference between those two fields. And again, this is something which has been mostly developed by Mark back then to train people understanding what they see in gravity maps. But today, actually, it's used quite a bit to train machine learning models. So in this context, PyNodi had a bit of a small revival because it's quite useful to quickly generate suites of different model realizations. Okay, can we use it for realistic settings? It's difficult, but it's possible. Here's a model on the top left of Gippsland Basin. So this is in Australia, a model by Mark Jessel, where you see that you have all these events interacting and overprinting each other to develop these quite complex models. Here on the right-hand side, you also see these multiple layers affected by multiple folding events and faulting and thrusting events. So that's possible, and we have seen actually some really nice cases. I'm showing you one more in a second here. And you can also use it directly also in Python for uncertainty quantification, using Monte Carlo error propagation or uncertainty propagation. So you see down here an entropy map for this model up here, where we estimate at least the uncertainty that we would assume is present here based on our kinematic model. So one just thing that I wanted to show is recent development by Noam Polak from Stanford University. She's been using PyNodi and Nodi to generate realistic models for her geothermal reservoirs. And this is quite amazing. She made two fantastic contributions, one in visualization here. So this is another type of VTK link, not PyVista. It's another VTK viewer, all part of the PyNodi repository right now. And she actually made a link to GIS, so you can extract interfaces from GIS and directly create a kinematic model out of it. So what is the state of Nodi? It's in PyNodi, it's fairly old. It's not going back to 2010, but to 2012. I think it's when I started working on that. It really needs a rewrite. So I see this point from what Leonardo meant before. But it's an open source project, so all contributions welcome. It's a bit of a pain to install, to be honest. This is based also on this underlying Nodi code that you need to run it. We are aware of that, but there's actually, it compiles quite well on Linux and Mac OS, and it has an executable for Windows. If you're interested in more details, we have a paper on it. I'll just post the link on Slack in a second. Where next? Because installation can be painful, as I said, we intend to write a wrapper for all the C code using PyBind. That's ongoing. It's a bit difficult because there's a lot of legacy code in Nodi as well. So it needs a lot of cleaning up, but it's coming. And we are looking at optimizing it a bit more for different types of machine learning training algorithms. Okay, and that's it. Short overview of PyNodi. Thanks for listening.
No, thanks for presenting. Really interesting to see when you're going to rebuild it all based on what we've learned this week. But
yeah, it will take some time.
We're a little pushed for time, so I'm going to have to let you go. And I guess you can
sure,
with any comments or
I'll post
questions
the links to the paper in
chat. But thanks for sharing some really interesting stuff. Great. So we're just about coming up to the end of the first session. We've got one speaker left, and then we'll be taking a short break before resuming on the hour. So our next speaker is Fabian, who I will bring in right now. Hi. We don't hear you if you're speaking.
Do you hear me now?
Yes, perfect.
Okay, good.
You're loud and clear.
How are you doing?
I'm good. I'm very much enjoying these surprising talks this morning. So
I just saw the one by Florian. So yeah, I'm gonna kind of follow up on that. He's actually a co-author in the project that I'm going to be presenting.
Great. Well,
just start.
You're right on time. So take it away.
All right. Cool. So as I just said, I'm going to be presenting or talking about a project that I did whilst being part of Florian's Institute for Computational Geosciences in Aachen. And basically, back then, we wanted to take GemPy and its capabilities of conducting structural geological modeling within a probabilistic framework and see how this and regarding uncertainties would maybe influence decision making. So I wanted to give the geological modeling and economic notion. So I created a synthetic geological model that would represent a typical hydrocarbon trap scenario. Here we have an anticline and a normal fault that would form this trap, and I assigned some uncertainties to the position in depth, to the layers, and also to the fault offset. And then I wrote an algorithm that would automatically determine where the spill point would be found, whether there's leakage across the fault or along the fault. And in the end, it would calculate the maximum trap fill of this structure. And this would then be our economic value of interest, because we can now take all of this and place it in a stochastic framework and generate many, many, many iterations of this model that are slightly different, and that will all produce a different result for a volume. So we will have a probability distribution for what a volume could be. And this will be the base for decision making, which we represent by using loss functions, kind of an experimental approach, because in the face of uncertainty, we can assume that we will never really know what the truth is down there in geology. And so the decision making process is basically estimating and allocating resources. And so we want to, if we assume that our estimate will be wrong, we want to be as little wrong as possible. So that's why we look at this loss function, and we're trying to minimize for the expected loss. So I kind of introduced some factors that would make this symmetric loss function asymmetric, and these assumptions would be about the problem at hand and also about the risk affinity that different actors or decision makers might have. So by doing that, here we see a normal distribution and the resulting plot below of differently risk-affine loss functions, and their minima, so their estimates of decisions, are found in different places regarding depending on the risk affinity. So here you can see that a risk-averse actor would put a much higher risk weight on overestimating than on underestimating. So he would rather tend to bid below the true value. And the risk-friendly actor puts a much higher risk weight on the potential of losing out on opportunity. So we found him closer to more positive values. And now we created different scenarios based on different states of information. The first one as a reference are simply our model with the uncertainties and how we produced different, we have this volume distribution, as I said, and this one is bimodal. So we have a high probability for the trap to be 0, so to be an actual failure. And to have some positive values, then we also have a higher probability. And the resulting distribution of our estimates based on these different loss functions and different risk affinities, they're widely separated. So the most risk averse here in purple, he would rather assume that the trap is a failure, and we find his estimate at 0. And the most risk friendly, he sees the positive, you could say. So we find him within the positive mode, so he would rather bid or maybe invest in this, whatever this might mean. And the risk neutral is found somewhere in between. And now we created different scenarios by adding information via Bayesian inference. So for example, by defining a likelihood function for the thickness of the seal. So now we assume something tells us hypothetically that the seal is actually much thicker than we thought, or it's likely very thick. So now we have a higher probability of the trap to be actually successful and there to be a good volume. So now we find that all these decisions or estimates actually move together, they converge, and the expected loss decreases. Inversely, we have this case where we added the information that the seal is actually thin. Now, all these actors move to, no, we're not going to invest into this because the probability of this trap being a failure is too high. And this third scenario is an example where we added a likelihood or some more certainty about the shale smear factor, which is dependent on other parameters, so it's more complicated. This actually, while it added certainty about the shale smear factor, it increased the uncertainty relevant for decision making. So you can see that the bimodality increased and decisions diverged and the expected losses of these actors increased. And what the conclusion of this would be is that whilst decision making, you have to try to understand which parameters are actually critical for your decision making, which actually add value for your decision making, and that not all the actors will gain the same benefit from one type of information. And we presented this form of decision making by a customized loss function as something that maybe might be a tool for recommending a best estimate, because it can also include the full range of probability instead of just looking at mean, median, and some extreme values. And yeah, so I bet this raised a lot of questions, and feel free to contact me on Slack or via this email. And yeah, thanks for the attention. Looking forward to the other talks.
Great. Thanks. Thanks for contributing today. We're going to go into a short break, so I'm going to let you go. But yeah, please follow up in Slack or with any of the speakers directly. And if it's piqued your interest in lightning talks, consider what you could present for 5 minutes, guys. So we'll be back at the top of the hour with our afternoon session, starting with Tony Hallam, who's been working on SegStack this week, and I'm sure has something equally exciting to share with us. And I will catch up with you in 5 minutes. Welcome back to the second hour of our lightning talks. With me is Tony, who's in Edinburgh, who's going to be taking us through what he's been up to. Without further ado, I'm going to hand it over to the young man himself.
Man. All right, I'll just share my screen. This one. Okay, you can see the notebooks. And I'll just, hello?
Yep, we can see your notebooks.
Okay, cool.
All great.
So today I am not going to be talking specifically about my work like a lot of the people that came before. I'm actually a PhD student at Heriot-Watt University in Edinburgh. But I want to talk a little bit about Dask, which is a great Python library that exists for scaling your code. It's a little bit similar to what Steve presented in his tutorial this morning with Ray. But from what I can tell, it's perhaps slightly better aligned to doing things with some of the native Python data objects that you use every day, particularly for large kind of volume throughput. It's kind of built on top of the normal scientific stack, so it integrates well with NumPy and Pandas and scikit. And it basically allows you to scale everything from your laptop. So I'm going to run a few demos today, hopefully, fingers crossed, with my laptop. But you can sort of scale it up to cluster size problems. And I also do this at uni. So I submit jobs to our compute nodes and distribute the work across multiple computers in distributed memory. So it's quite good for that kind of thing. And it's very customizable. So you can see, like here, for example, a number of the different libraries that kind of sit underneath Dask and have been used by Dask to scale. So if we go to the notebook, I was going to present something else, but I've been having a bit of fun with the SegWySac project, and I was going to just run through a few examples of things you can do with larger volumes in SegWySac. So one of the nice things that SegWySac does is it will convert your data to HDF5. You can load your HDF5s with Xarray lazily so that the data remains on disk, and that can be pretty crucial when your seismic volumes are quite large. Dask also integrates pretty well with the Jupyter Notebook, and it really excels at interactive computing. So here I'm just starting up a little cluster here, and they call it a cluster, but it's basically a number of workers here on my laptop with some memory assigned and some cores to work on. You can dynamically scale that. So for example, here we can scale the cluster down. This memory limit isn't a hard limit, but it reduces the memory footprint and the number of workers that are available. You can access a dashboard that comes with Dask, and I saw Rapid said something similar. You don't need Node for this. This is built on top of Bokeh. So you get it for free with Python, basically, even though it uses Java in the background. There's also a nice little Dask extension here, so you can see you can kind of pop these little toolbars out, which give you kind of information about what's going on with your cluster as you run operations. The key thing about loading data in with Xarray is that you specify some chunks. So this basically allows you to brick your data, and it means that Dask knows to load things lazily. So we're looking at a 2.14 gigabyte volume on disk, but you can see that was instantaneous. So it basically just scanned it to see what the dimensions were, and then automatically calculated the chunk sizes. So you can see I've got 4 chunks in the inline direction, 5 chunks in the cross line, and 1 chunk vertically. When you chunk data in like that, it doesn't actually load it in. So you can see Dask creates these kind of pointers to the data on disk, and you don't necessarily have to actually load all that into memory. You can see I'm only using about 100 megabytes here at the moment. So what happens when you want to do some computation? So a lot of the things that you would normally do with Xarray or you would do with NumPy are all applicable to Dask arrays. And Dask creates basically those large computational graphs and then executes them only when you ask for that information to be executed. So it will load information on the workers individually, and then you can either reduce and map reduce that information, or you can even output the information directly from the workers. So in this case, I've asked for the mean, but the mean is actually nothing at the moment. It's just basically a computational graph that Dask has calculated. And you can kind of visualize what that graph looks like. So here we've got basically the start of the task, the loading of data, and then basically successive accumulations of the mean value down to a single output. And when you calculate that, that graph is kind of executed here. You can see it sort of split the graph up into the different chunks, run the process, and then return the mean back to me. And you can do a similar thing for plotting. So here I'm just calculating the standard deviation to scale my data. And the nice thing here is that Dask will only pull in the data that it needs for plotting. So it's not going to load the whole seismic volume, even though I ask for an inline, a crossline, and a slice. It's sort of going to do that independently. And this slow bit at the end here is actually just matplotlib. And so we can get some nice plots. You can do more complicated tasks. So here, for example, I'm doing standardization, just subtracting the mean and dividing by the standard deviation. This is going to take a little bit longer, but you can see Dask works this out and then sort of processes through that graph slowly. And this is running now on the 4 cores of my laptop. The good thing about this is I'm not actually going to fully load all this data into memory. Just going to output directly back to X-ray on disk. One thing to be aware of is don't use the delayed decorator and Dask collections. So that includes like X-ray chunks and so forth. That'll cause a lot of problems. Not going to run that. And the last one I wanted to show here was a quick example where you can apply, for example, a function to a trace. So we're just going to apply some linear gain to a trace. This hasn't been calculated yet. I've just sort of started to create the graph. You can see the way that that graph basically is going to be applied. And then we can assign that data back to our original data set. And again, we can see that that data now is just a graph sitting in memory waiting to be computed. And it's not actually until we call the 2net CDF that it actually starts to chunk away on that.
Yeah, I'm afraid you're running a little over time, Tony, so I'm going to have to
sorry.
cut. I know everyone loves a bit of Dask, but and I guarantee that you'll be giving a much longer tutorial on this later.
Yeah. Sorry about that. Yeah. Anyway.
So yeah.
Thank you.
But yeah, funnily enough, I first encountered Dask at a hackathon a couple of years ago, and it blew my mind then. And seeing it like this now is really good. But thanks for the great overview and the nice seismic images and dashboard. I'm sure people have got questions. I fully expect there to be a T20 Dask channel soon, or a Software Underground Dask channel. But
yeah, my
thanks
pleasure.
Thanks for speaking. And again, in the interest of time, I'm going to move on to our next speaker, who is Santiago, and bringing in right now. But yeah, it's always great to see new tools or old tools that you've only seen once or twice being used properly. So, hello. You will need to unmute.
Hi, Dan.
Good.
Can you hear me?
Yeah, hear you loud and clear. Good day.
Okay, awesome.
Haven't got much time to kill here, so I'm going to hand it straight over to you for your 5 minutes.
Okay, thank you. Let me share my screen, I think. Oh, where is it? Okay, let me try with this and move here. Can you see the slides or not?
Yeah, gridding grav mag data with harmonica.
Okay, great. So little introduction first. I'm Santiago Soler from Argentina. I have a degree in physics and now I'm doing my PhD in geophysics. I work mostly with potential field data and trying to develop new methodology, and that's the core of my research. So I think Leonardo had introduced me a little bit earlier. So I will move on with the slides, I think. So I want to show you a little example on how to create gravity and magnetic data with Harmonica. Harmonica is a library that is part of the Fabian Stamm project. And in this example, I want to show you how we can use it to grid gravity and magnetic data using the equivalent layer or equivalent sources technique. And also, I want to show you how we can use the whole Fatiando ecosystem to do so. So first, what is the equivalent layer technique? Basically, it consists in a technique that allows us to obtain a regular grid from a scattered point. So for example, you measured gravity on a scatter of points, and it basically consists in defining a set of sources below the data and use these sources to predict on grid points. Okay, so let's get started by importing some libraries that you might be familiar with, and some Fatiando libraries as well as Bool, Verde, and Harmonica. We can start by downloading the data we will work with, some South Africa gravity data. This looks like this. And for this little example, I want to reduce the computation time so I can downsample the data using Verde. So now we can see that we have much less data points than before. Then instead of gridding on the absolute gravity, I want to grid the gravity disturbance. So I need to compute it first. And I can do it through Bool by defining our ellipsoid and then telling the ellipsoid to compute the normal gravity and removing that normal gravity from the data. So that's what the gravity disturbance for South Africa looks like. And finally, before getting into the actual gridding step, I want to project the coordinates, the lat-long coordinates we have from the data to north and east in meters, and we can do that through the PyBrush library. So this is how the projected coordinates looks like. So let's get into the gridding, the most interesting part. So we can start by initializing the gridder, the EQL harmonic gridder, with some random values for the two parameters it needs, the relative depth and the damping. And then we can fit the gridder by passing the data we have pre-processed. And then we can tell the gridder to actually predict the gravity field on a regular grid, okay? That is at a constant height. And we can see that we had not so good looking grid. Basically, this grid doesn't reproduce the high frequencies of the data, and that might be because of the bad choice of the parameters. So how can we improve that? How can we choose a better set of parameters? And we can do so through cross-validation. And we can start applying cross-validation by defining a set of values for the two parameters the gridder needs, and then generate a combination of every possible combination of these two parameters. So then we can apply cross-validation through Verde. So basically, for each set of parameters, we can apply the cross-validation through the gridder and score it, get a score of the gridder, okay? And as you can see, we can use Dask for we can use Dask for distributing the whole process and make it faster. That's awesome. And we can finally get the best set of parameters that achieves the best score and use that for actually gridding. So we end up with this better looking grid that actually reproduce the high frequencies along with the low frequencies of the data. But we can see that some grid points are very far away from the data points and the predictions might be not so accurate. So we can use Verde for masking those points and end up with this pretty nice looking grid. And finally, for finishing, I want to show you that these griders doesn't work only for actually gridding into a regular grid, but we can use them for predicting gravity values on any point, any point we want. So for example, if I want to get a profile along a certain line, instead of getting the grid and interpolating the grid, I can actually use the gridder for predicting gravity values on the profile points. So we can do this very easily through the profile method of the gridder by defining 2 points, and we can end up with a profile that is not interpolation of the grid, of the grid, but it's actually a prediction of the grid. So thank you very much, and you can download this notebook if you want. We have a Fatiando repository for it.
Great. Thanks for presenting. It's really interesting to see the different pieces of the projects coming together in one complete environment. So how long have you been involved in the software underground, Santiago?
I think from when I started my PhD in 2017. Yeah, so 3 years.
Fantastic. And have you been working on anything this week other than your presentation, or have you been hacking away?
This week now, I think mostly the presentation and helping with the Verde tutorial. But the previous weeks I've been trying to research and how can we make these greetings faster and less memory consuming. Because as Leo pointed out in the Verde tutorial, these require a lot of RAM if you have a very large number of data points. So we are trying to research some ways to trade computational time for memory. So you wouldn't need 1 terabyte of RAM for greeting.
Great. Right, I'm going to have to let you go because our next speaker is messaging me, desperate to get in and give his talk. But thanks so much for the information, and yeah, follow up in Swung if you can.
Okay. Thank you, Dan.
Thank you. So next up is Doug from the UK. Funnily enough, I met Doug at a hackathon almost a year ago, I guess, one in London that Filippo and I organised. And he's an enthusiastic coder. I think some of you have been hacking maybe with Doug in this Dash project, but I'm very excited to see what he's going to share with us today. All right.
Hey, Dan, can you hear me?
I can hear you loud and clear, Doug.
Perfect.
The floor is yours to do with as you please.
Awesome. Let me just share my screen.
Yeah.
Okay, so I guess this talk is a little bit different from some of the previous talks in the Lightning sessions today. So I don't really have a project I've been working on to show, but really this is a pitch for some ideas and some thoughts on a new idea or a follow-on from some existing ideas that exist in the software underground. So I guess there was a conversation with Lisa Streit a couple of weeks ago about using seismic attributes for analyzing subtle stratigraphic changes. And it kind of relates to a seismic forward modeling project that she was working on. And it led to a whole bunch of follow-on conversations between Alessandro, Steve, myself, and a few others, kind of on how we use 1D and 2D synthetic seismic modeling to kind of help out with some of these issues that Lisa was talking about, and how we don't really have a really great open source tool that does some of the things we'd like it to do. So in particular, kind of what we really want is something that's got the ability to help a geologist or a geophysicist take something that's in their head or something seen in a paper or an outcrop or something visually that they can make into a synthetic seismic section in a few tens of minutes rather than a few tens of hours in some of the commercial tools that people are using at the moment. And I guess in that discussion, we're aware that there's a whole bunch of things that exist at the moment or have been done in hackathon projects. But kind of what the idea we had was, it'd be great if we could try and wrap these things together in a kind of a unified synthetic seismic modeling tool for interpreters. So I guess what we thought would be really awesome is if we had a tool that could do a whole bunch of different things, which is both qualitative and quantitative on 1D displays and individual logs, on 2D displays, whether that's geometric models, whether that's figures from published papers, whether that's quantitative, EI or impedance models, and also potentially the scope to move into 3D models, taking things like 2D sketches of outcrops and trying to extend them like you would do an object model in a Petrel type modeling workflow, and also whether or not that kind of whole 3D backward simulating seismic from existing Earth models again might be something that could be interesting. So what I'm going to show is a couple of examples in the next couple of slides of the kinds of things that we quite like and whether or not there's scope to try and build on these as an open source tool. So I guess when we talk about 1D synthetic modeling, most people are probably quite familiar with the idea you can see in the top left here of a synthetic well tie, trying to tie your log data to the seismic data. But I guess 1D logs can have a whole bunch of different purposes. You can see in the bottom left here, there's an example of a what if impedance display. So what kind of attributes can I make from my well data that allow me to best discriminate those different fascies from the seismic data? In the middle section, there's an example there of how you parameterize Backus averaging on your well logs to kind of optimize your quality of tie to the synthetic seismic data. And then in the far right-hand side, we've got a few examples of how you can make layered models from what-if scenarios of sand and shale combinations that would give you similar looking synthetic seismic responses. And it helps you to understand what some of the uncertainties are in trying to predict rock properties directly from seismic data. And then when we talked about synthetic 2D modeling, we kind of had two themes. We had the idea of geometric models, so dipping layers or wedges or domes, things we can use to look at very simple relationships. So look at a tuning wedge for the impact of a bandwidth in the wavelet in terms of how much tuning you have on an amplitude extraction, or to look at lateral changes in rock properties or lateral changes in fluid properties to help interpreters understand what kind of amplitude changes they should expect to have under different fluid or rock type conditions. And then the thing that really we want to get to is realistic 2D synthetic seismic models. So you can see on the left-hand side, there's a published example from, again, from Lisa Streit, looking at some of the turbine outcrops in Black's Beach. And then on the bottom is an example I'd worked up a couple of years ago on some flavial outcrops, this time using a free tool called modeler.io that Matt and the guys at Agile had built a couple of years ago. And the nice thing about these synthetic 2D models is it really gives the interpreter the ability to make a catalog of known seismic geometries based on known outcrops or published examples. And they can really use that to understand the things they should be interpreting from seismic or the things they maybe shouldn't be interpreting from seismic data. And the real kind of blocker we have at the moment is that a lot of the commercial tools available, it takes a lot of time to construct those detailed shapes to make a model from. It's not really easy to just draw a sketch and then make a model from that sketch. And in terms of 3D synthetic seismic forward modeling, I guess as far as we could understand, like people not really doing that for how an interpreter uses seismic data to guide their interpretation. Like synthetic seismic modeling in 3D tends to be all focused around understanding complex seismic imaging, FWI, RTM, maybe 4D synthesize, that kind of approach. So I guess we're quite keen to hear from people in the audience if they've got examples of anyone using synthetic seismic 3D modeling also as an interpretation aid. You know, an example I'd quite like to be able to do is to basically take a 3D rock model of a deep water channelized turbidite system, you know, put different wavelets through it and understand in 3 dimensions what impact the interference has on some of the amplitude extractions. And again, the question we had potentially is GenPy something we could use to make these kinds of models. And then we had one more thing that kind of cropped up in the conversation is, you know, almost all of the seismic modeling we see at the moment is based on 1D convolution. And I guess it's great for making simple models, but it maybe doesn't really represent what real seismic actually looks like. So then there are some options out there for kind of point spread function type models. And it's a question kind of for the software underground is, tool like DeVito or Pylops, is it possible to use those kinds of tools alongside a normal 1D convolution to make more realistic synthetic seismic forward models? As you can see in the left-hand image at the bottom there, as you start to look at different point spread functions, you start to understand more what a migrated seismic section look like, and less like just 1D convolution.
Great, you're just at time, Doug. So hopefully this is your last snapshot.
I guess the last one I can do in this, which is, we're aware that a lot of these tools already exist, but really what we're interested in is trying to, get the useful bits out of all of them and combine it into a tool that's accessible to people to do synthetic seismic modeling quickly and easily, and feed that into how people make seismic interpretations. That was me.
Great. No, thanks. Thanks for sharing something very different to what have you been working on. I'm going to ask you one question. That's how have you found your journey from geophysicist to kind of getting into the world of code and machine learning? Because I think when I first met you, you were starting out, and now you're leading hackathon projects. It's
well, I think leading hackathon projects is maybe a bit strong. So I'm maybe the person that's trying to collate together some of what everyone's doing. But the thing I've enjoyed most about the hackathon this year is, like, I've been in a team with people of lots and lots of different skills, and I'm still quite at the beginner end of that spectrum, but we've worked really well together as a group, and it's been really great to learn a lot from the tutorials in Transform this year, but also apply that in some of the stuff we're doing on the hackathon project. So yeah, not sure I'm quite leading the project, but I think it's been great to collaborate with a bunch of people with a whole bunch of different skill sets. So yeah, it's been good.
Great. No, thanks so much again. We're just running tight to time again, so I'm going to have to let you go.
No
but yeah, catch up with Doug. Really great stuff from this and the hack. And we'll now move on to our next speaker, who is also equally keen. As soon as I was hosting, Andrea was DMing me saying, "How do I host? What's the protocol?" So let's bring her in right now. Hi.
Hello.
Are you ready to present, or would you like me to do a bit more vamping?
I think I'm good. I'm sorry, you were cutting off with the video that I had on. I'm good. I'm good to start.
Great. So I'm just gonna turn myself off, and I'll be back in 5 minutes to ask you some questions.
All right. All right. Okay, I think I'm good to start. Thanks, Dan. I didn't see that I was live. So my name is Andrea Balza. I'm here to present a project that I'm very passionate about. I've heard many great talks today, and this one is definitely different. I want to talk about our Geolatinas coding group. I am Andrea Balza. I'm the presenter. I'm a geophysicist who specializes in potential fields. I'm here in Denver. And I'm not alone in presenting this talk. I would like to honor my team, Isamar Cortez, who's the leader of this initiative. She's from Puerto Rico and works as a NASA fellow in Montclair University. I'd also like to acknowledge Angelique Rosamarin, who's sort of the logistical hand, and is also from Puerto Rico, and she is a NOAA CCME scholar in Florida A&M University. Our founder, Clara Rodriguez, and our co-founders, Rocio and Adriana, for creating Geolatinas and making this group possible. And this is a group effort from more than 220 members around the world. So what is Geolatinas? We are an international organization that promotes, welcomes, and empowers the work and research of Latina women in earth and planetary science. Our mission is to promote, embrace, and empower Latinas' work and provide tools to help Geolatinas succeed. So this is where the coding group comes in. We want to provide tools to help Latinas thrive in their careers and their research. We also want to inspire future generations and foster curiosity about Latin Americans and our rich culture. We want to distribute information on education, scholarships, and job opportunities to help bridge the gap between these Latinas and these opportunities. So our group is divided into six different groups as well. It's all member driven, it's 100% volunteer based, and the core of this organization lives in the Leadership Council. So I think it's important to recognize why a group like Geolatina should exist. We need to promote, I feel, more women and more Latinas in this industry. In Geolatinas, we're not only identifying these statistics that we see here that we've probably seen before, but we're striving to make a change, and our mission is to increase the participation of Latinas in these leadership roles and help them enter uncharted territories. So one thing that really stood out for me from these statistics is Latina made up only 1% of the computing workforce in 2017 and 2% in 2019. I mean, we're increasing, but it's at a very disappointing rate. So in Geolatinas, as I said, we're a member-driven organization. We give our members the leadership spotlight for them to experience leadership and being comfortable in managing an initiative. We sort of give them the torch and say, run with this idea and we'll support you. So in this council, we have many initiatives. And the one we'll talk about today is the personal development, where the coding group started. Here's some stats about our demographic. I would like to include that we are an inclusive membership and we welcome any race, gender, religion, etc. into our group. And so now we'd like to present our beautiful coding group. It's 2 months old, but we've done a lot for 2 months. Here you can see us gathering. This is Isamar, Angelique, and myself. This group was born to teach our members about the importance of open source coding and how it's become sort of a really good tool to have as a geoscientist. We want our members to be part of the playing field and not only use these codes, but also develop them themselves. So all of this is online, very similar to what Swang does. It's a virtual community. And our sessions are in Spanish, but as you know, most of these codes are in English, so then it becomes sort of a Spanglish mix. And we look forward to having some sessions in Portuguese once we have a Portuguese leader. So we use 3 different platforms. Jupyter, Google Colab, and Spider. And we have live twice a week coding sessions. We also use these Slack channels where that's most where our conversation is fostered. And in these live twice a week coding sessions, we have one on Mondays and on Fridays. We introduced this theme on Monday and practice on Fridays. And so far we have seen NumPy, Matplotlib, and Pandas for the month of June. We have shared resources and our very own Geolatina hackathon, which I'll talk more about later. And we gave it our own personalized name called GeoHackeo. All right, so, and we also have a Geolatinas GitHub. So our coding group goals is to teach our members about Python and R. And after seeing all of these great talks about JavaScript, I think that would be something in the works. We want to motivate them to start programming and give them a comfortable space to show that coding may be hard and overwhelming at the beginning, but I feel that our live coding sessions are a great, wonderful space to welcome any beginner and sort of a fun dynamic to give the Latinas the resources to advance in their careers, which I think is important. So our Geohackeo projects are going to be focused on creating tools to help our volunteers automate tasks. So we're going to start on June 26th, and during a month, we're going to develop codes to help automate our membership tasks, so to help volunteers save time. For example, our great Chief Operating Officer, Carolina Villarraga, is managing all of the data of our memberships, and we want to create tools to make her save time and make this easier using Python. We also want to analyze statistics to present research about survey that we have right now called Voice Your Needs, and present this in a very informative and a clear way for our members to see. So how to collaborate in our coding group if you're interested and inspired by this initiative. You can share Python and R resources. You can become a GeoLatinas member and join our Slack channel. Create webinars with general modules packaged to support our goals. I think the tutorials that were given in Transform 2020 are a great initiative for us to look at and start. Collaborate with the logistics of hackathons and future events. Our Geohackeo is during a month, but we are planning to do future hackathons that focus more on our research. And help create coding materials. There's also a way how to get involved in GeoLatinas as an advisor, as leading initiatives in projects if you are a Latina in geoscience. So with that, I would like to thank my my great team, and thank you, Swang, for organizing this. I see you guys are a very forward-thinking and open group, and will understand the importance of diversifying a workplace. So thank you for that.
Thank you. Awesome talk. Really nice to see initiatives like this going on in the space. I'm really glad that you chose to give a lightning talk on it, because you know I'm based in Europe, so I would have had no idea that you're doing awesome stuff like this. There's some excellent comments in the channel, like people are really impressed. So Matt said,
Yay.
as Matt Hall said, yeah, live coding sessions are a fantastic idea. I'm going to have to let you go to put us back on schedule and get our next speaker in. But thanks so much. Really, everyone, this is a great time to talk about this kind of stuff. So thanks again, and enjoy the rest of Transform, and good luck with the initiative. Probably goes without saying, everyone here will jump at the chance to help you.
Thank you, Dan. Thanks. We look forward to presenting in Transform 2021.
Great. I'll put you down for another lightning session.
Great.
Great. So next up is Rowan, who has been patiently waiting here for a little while. Let's get him in. Yeah, I mean, that's been one of my favorite talks so far. It's what I like about this. It's just an unexpected journey of discovery, and whether it's code, new initiatives, or new ideas. And here comes Rowan now, right on time. You are muted, so you will need to unmute.
I could do this on mute if you want. Maybe.
Sign language. I tell a lot. You have 1 minute before you want to start. So if you want to give any opinions, facts, or jokes, go right ahead.
Oh no, I can't do that.
I see you preempted my question about membership. So.
Yeah. No, I had to look back in the Software Underground Slack log. So if people want the exact UTC time that they joined Slack, that is actually in there.
I have this big theory that 2018 was the year that suddenly Swung kind of exploded, or at least to me it was. And it's always interesting to see, you know, who's been around the longest, who's been around the shortest, and kind of what they're up to. So it brings us nicely to the start of your talk. So I'm going to shut up and let you get on with it.
Cool. So I'm Rowan Cockett. And I've been working on a few projects that you may recognize. So visible geology, SimPeg, 3-point science, and a new icon that I want to talk about a little bit today. which is sort of about moving ideas forward and some brief thoughts on writing. So where I want to start is a day in the life of an equation. So this was an equation that I was working on during my PhD for Vadostone fluid flow and inversions for hydraulic parameters. And this was the derivative. And sort of as with any idea that you're working on for many, many years, it sort of shows up in a multitude of places throughout your work. In your notebooks, when you're coding, in documentation, in presentations, in papers, in your thesis, as well as in other places like your blog. And as with any idea that you're working on for a long period of time, you want to make changes to that. You want to improve the clarity and the presentation of that idea, even if it's simple pieces. Those changes are helpful in communicating those ideas. And what I wanted when I was working throughout all of these different repositories and these different places that I was working was knowing how this idea is updated, is changed, is different than sort of this core concept that I was developing. And unfortunately, the sort of copy paste style that we sort of find ourselves in writing, it doesn't come with versions or diffs. And that's even the case if all of these projects are under version control. And I feel like that's annoying enough to spend some time on. But I think there's this sort of secondary piece that's unfortunate because it doesn't separate things into this feedback loop between develop and use, which we're quite familiar with in the open source world, seeing like Leo's package of Fadiando, and that's like a decade old of these sort of ideas that are being iterated and developed in place. And so what I'm sort of posing here is what would an import statement look like for your scientific and your technical writing, for equations, for figures, for tables, even for things like paragraphs, and how does that change and how can you get notified about all of these things across all of your work? And this is sort of this other question of how do we reuse ideas and move them forward together? And in the open source programming world, I think we're doing quite a good job of this as a community because we start with an open license, and that says that you have the ability to use this in other places. And we can discuss what's wrong or what needs improvement with these ideas, these packages. And we can fork it because it has those licenses, and we can work on it without permission, and then we can have sophisticated tools that allow us to merge these changes back in. And we also have package managers that allow us to import work and reuse it and get notified of updates. And in writing, I think the state of play is quite different. The default is copyright, and in the academic journal system, it's paywalls. I think we're doing comments actually pretty well, especially when you're creating documents. And because we don't start with a license that's attached to our work, when you fork it, instead, you're actually, that's sort of the social thing that we've said is plagiarism instead. And merging an idea is extremely difficult because we're manually copying and pasting and updating. And instead of importing a package or of that sort of idea, we're often starting from scratch. And so what I want to think about here is how do we bridge that gap between programming and communicating? And computational narratives in Jupyter are this sort of huge step forward, but it's still really too hard to version and remix, share, integrate, import, and work on these ideas together. And so what if each block was versioned? What if it came with comments and updates that you could see and merge in context in the tools that you already use? And so this is an idea that I'm working on my new startup called IOXA, which is an integrated version control system for your ideas wherever they live. And so this is a new idea, so please reach out if you're interested in any of the stuff that I've shown. Go to ioxa.com or ping me on Slack. So thank you very much.
Awesome. Yeah, thank you for the lightning pitch, I guess. So how long has the startup been going? Is it brand new?
It's like officially 2 months old. I've been thinking about these ideas since way before my my PhD. So like the last decade, I've been sort of thinking about reusing ideas and how that actually works.
Awesome. And yeah, so what have you been working on this week? Have you been hacking at all, or have you been doing anything grabbed you kind of from Transform?
The Gostin project, I've definitely been keeping tabs on, and I was trying to help out with the workflow examples piece and getting that survey out. So there is a survey in the T20 like or somewhere on Slack that you should help fill out and get some workflows to us.
Great. All right. Once again, our next speaker is very keen to get into the meeting room, so I'm gonna have to let you go.
Cool.
But yeah,
All
feel
right.
free to reach out. I mean, this looks awesome. Version control. I know there's a certain Norwegian that I know on Swung who's very into version control. Will find this awesome. So you've got at least one fan
Thank you.
here. And good luck. Yeah.
Cool.
All right. So our last speaker is Artash, who I think is probably one of the youngest members of Software Underground. And he's joining us from Canada. Artash has been leading a hack this week, I believe, on some very cool seismic data, looking at how basically COVID-19 has reduced traffic due to seismic data. So, hi Artash, you'll need to unmute.
Hi.
Great. So, how are you doing? How are you enjoying Transform so far?
Well, in fact, I'm really enjoying the Transform Hackathon because it's my first geological hackathon, and I've been so interested to see the amount of data sets that I can get through libraries like OpsPy and analyzing them. And there's a great community on this hackathon that I can reach out for help. So everything's been going great.
Fantastic. And how is your project going? Because I believe you pitched quite an interesting project at the start of this.
Yeah, my project is going pretty great. So I've been able to use all the tools suggested to scrape seismic data. And in fact, yeah, I'm going to be talking about this project, I think on Sunday. So I'm doing pretty good progress on that. Thanks.
Great. And what are you going to be talking about this afternoon?
Yeah, well, since in the past, I've been attending lots of space exploration related hackathons. Today, I'm going to talk to you about one of my recent projects to do with AI and space exploration. In fact, it is to remove the noise from exoplanetary observations using artificial intelligence.
Fantastic. You've got about one more minute if there's anything else you want to fill in the time with before we start, or else I can go back to my list of questions.
Huh. Sure. I'll just, so the share screen, I'll share screen right before.
If you want to get set up in this time, that's perfect.
Sure.
It sounds like a great talk. I wouldn't have thought to use machine learning on exoplanets. There's a friend of mine who's doing their PhD in astrophysics. I'm sure they'll find this kind of talk really interesting. Yeah.
Oh, that's cool.
But we have quite a few planetary scientists actually lurking in Swung, so I'm sure you're gonna be very well received.
Thank you.
Yeah. I'm trying to think. I think my first hackathon project was predicting what was ahead of a drill bit, and my sole contribution was providing food to the actual programmers at that time. So you're doing very well for yourself.
Thank you.
You're coding up. Yeah. So if you want to share your screen, we can start shortly.
All right, can you see my screen?
Yeah, fantastic. Great. Yeah, we can see your presentation. It's full screen, and we're now on time. So I'm going to hand over to you, and I'll be back at the end to ask some questions.
Thanks, I'll start off then. Hi everyone, I'm Artash, and I'm a grade 8 student from Toronto. I'm very interested in space, robotics, machine learning, and I love learning new things. I've been to many hackathons in the past, mostly to do with space exploration, AI, and robotics. And in fact, this is my first geological hackathon. So today I'm going to be talking to you about my project of removing noise from exoplanetary data using artificial intelligence. So for those of you who are not very familiar with exoplanets, just like our Earth orbits around our sun, exoplanets are planets that orbit around other stars in the galaxy or the universe. So I'm going to show you a quick video on how we can detect these exoplanets.
Let us assume that my face is a star, and this is an exoplanet. When the exoplanet passes in front of me, some part of my face will be blocked off. So if I was a star, my brightness would decrease. Let's say we have a new exoplanet here, and this one, as you can see, has an atmosphere around it. So if this exoplanet passes in front of the star, the decrease in brightness will be slightly more.
Stellar spots add noise to the data by changing the depth of the light curves.
Let us assume.
So these stellar spots that you saw in these videos, stellar spots are places on the surface of a star that are slightly dimmer than the rest of the surface. So when I was talking about atmospheres, since exoplanets have atmospheres around them, and we're measuring this dip in light in several different wavelengths, there'll actually be a slight change in the depth of the dips for each of this wavelength, because for some of the wavelengths that are emitted by the star, the exoplanet's atmosphere may absorb, making it look slightly bigger, or it may let them pass through, which will make the exoplanet appear slightly smaller. Now, these changes are very small, and these stellar spots can also cause these small changes in these light curves. So we need to make sure that the dips we're seeing because of the exoplanet atmospheres are because of the atmosphere and not because of the unwanted stellar spots. So I wanted to find a way to remove these stellar spots to allow us to accurately measure the dips in light for each of these wavelengths. For this, I decided to turn to machine learning. So this is the data set. In the data, there's inputs and outputs, or there's a training and testing database. In the training database, a machine learning algorithm that I would implement would learn how to remove this noise. And in the testing database, I would see how good it is at removing this noise. So the inputs obviously were the light curves in all the wavelengths, and the outputs it had to predict is these dips in lights. So to do this, I implemented a hybrid machine learning algorithm. So it took two different inputs. It took the light curves, so these were time series data that were observed, and it also took numerical data. These are just a couple of different numbers. So for example, the orbital period of this exoplanet, or the temperature of the star, or even the radius of the star. And these are very important tools that we can use for the algorithm to detect or remove the noise. So this is a hybrid machine learning algorithm. So the time series data, which is the light curves, pass through a long short-term memory network, which is a type of recurrent neural network that's good at analyzing these sequences, such as light curves. Then the stellar parameters go through two dense layers, and then the outputs of these two subneural networks get merged together to produce a final output, which will be the planet to star radius ratios, so kind of like the size or radius of the planet in all these different wavelengths. So this is the loss and accuracy graph of this hybrid machine learning algorithm in orange, and you can see it reaches a pretty low mean squared error. So this just took 3 hours of training, and these are the results. So since we were observing in 55 different wavelengths, the orange graphs are the ones that are predicted by the network, and the blue ones are the real planet to star radius ratios for these wavelengths. Now, this project took a lot of AI part, and I in fact created a tutorial that you can see on my GitHub, and this will in fact walk you through the steps of making your own kind of neural network that you can apply to these atmospheric data. Now, this project used machine learning to remove the noise from these things, but this can also be applied to seismic data. Now, seismic data can be very important because such as an experiment such as the LIGO, which serves to detect gravitational waves that come from the merging of black holes, the LIGO has to be very stable, and it's very sensitive, so other seismic activity should not affect this measurements of the LIGO. Seismic activity data is also very important in other cases. For example, even in space exploration. For example, the NASA's Mars InSight mission, which is a lander on Mars, is going to collect seismic activity from Mars's surface. So even here, we will have to use tools such as machine learning to isolate the vibrations and analyze what are the important vibrations we're sensing from Mars's surface. Thank you. And if you have any questions, I'll be glad to answer.
Oh, thank you for the great talk. It's really interesting. I've never dealt with astrophysics before, but just great. So what started you on this passionate journey, kind of into this space and ML space? Because when I was your age, I was busy, definitely not doing this stuff this interesting.
Yeah. Well, in fact, I think this started when I was around 8 years old. So we had a telescope, and sometimes I would gaze up and observe different stars of my interest or different constellations. And this got me really interested in astronomy. And I also joined the Royal Astronomical Society of Canada, which is a big astronomical group in Canada. And I learned much more about planets and exoplanets and other stars. And my passion for machine learning also came because I love tinkering and making small robots. So I decided it would be cool to automate these robots. So I decided to learn machine learning. And then these sort of came together, and this project was ideal because it used both machine learning and space.
Awesome. Now I can relate to that because I've just built a robotic lawnmower that learns the pattern of my garden through machine learning. So that was a fun little project. Yeah. I'm definitely going to check out your tutorial because it's just really cool. I'm really, really impressed, and I think everyone here is. But yeah, thanks so much for volunteering a hackathon project, volunteering a lightning talk, and putting together a free online tutorial on machine learning. It's really great. So really hope you're going to enjoy the rest of Transform and stick around the software underground. And make sure you talk to Diego because he's a fellow enthusiast of machine learning and space. So yeah, but no, thanks again. And if you've got any final words before we let you go, feel free.
I'd just like to thank the whole community that put together this event, because this seems like this is the first time that this event has gone online. So it's great to see that the event has turned out so great.
All right. Thanks a lot. Have a great day.
Thanks. You guys too.
Great. And now joining us is the man whose fault it all is, I guess you could say, Matt Hall. But yeah, I'll say, as much as we love putting together events and emceeing and whatever, it's you, the audience, and the people who participate who make it very real. And I think this is something Matt always says, is there is no transform without people transforming things, willing to be transformed, or getting their hands dirty, breaking things. So we're just going to kind of sum up what's gone on. There's the hackathon begins again tomorrow, bright and early, with my good friend Filippo and many of the speakers you see here today. We have one more tutorial today with Matt and Brendon. And of course, everything else is available on Catch Up. So I'll hand it over to you. You're on hard mute, I think, Matt, because you're unmuted in the meeting, but no sounds coming from your end. Yeah, I can just about hear you there.
Is that better?
You're yeah.
I don't know how to. I could just sort of switch around different mics until something sounds better. Yeah. Vaguely good. Yeah, amazing. Thanks, Dan. Thanks for doing that. I know we kind of dropped you into that. I asked Dan if he would. I can't remember how I put it, but maybe.
What I remember is you said you just have to turn up and introduce the speakers, and then I said sure, and you said, "Oh, go on," and then you read my message and it's like, "What? You've actually agreed, you fool?"
yeah, it's just 4 hours of emceeing talks that you don't know the titles of in essentially random order. So yeah, no, you did awesome. Thank you.
It's my pleasure.
It's so great. These lightning talks have been such a whirlwind. It's just like one thing after you're just digesting one thing, and then something else comes along that's you know, out of a completely different bit of the space, you know, just learning about the variety and scope of the things that people are into is really fantastic. Nice t-shirt, Dan, I like that. And yeah, I think Brendon said something to me in the chat just now about sort of capacity, the capacity that we're sort of seeing in this community, and that's what, you know, that's what I keep coming back to. Is, I mean, that's our purpose here, is to sort of create the capacity in subsurface science and engineering to do awesome things with digital data and digital tools. And, you know, seeing a grade 8 student with the imagination and you know, skill and personal capacity to even start taking that on, to me just affirms how important this is for society, for you know, for the future of energy, materials, understanding our environment, even space exploration. You know, we need the natural sciences, and we need them to be as digital as possible. So that's our, you know, that's our mission. If you need a personal mission and a reason for sort of personal transformation, there it is. I wanted to put something right that I've been kind of neglecting, which is thanking our sponsors. They've been up on at the beginning of every video, but I just wanted to call out Dell Technologies. Many of you probably know or have at least conversed with in Swung. David Holmes, he's been a relentless and long-time supporter of what we've been doing. I think since, I'm going to say, the 2017, was it 17? Anyway, the one in Austria, in Vienna, the gaming hackathon, where we saw, what was it? Flappy Trace from Lucas Mosser and co, and some sort of amazing Tetris game that Jesper built.
Yeah, Larson is very proud of his gully attack game they made, shooting the gullies in Parry Hacker.
Yeah, right. And then we had that. That was just in Stavanger a couple of years ago. Yeah. And AWS Technology, AWS Energy, I beg your pardon, have recently donated a lot of compute, which Steve and Filippo are making accessible to the community, and we're going to try and explore some different ways of doing that as well. So stay tuned for more about that. And then Nthought and Agile as well for supporting this event, for supporting Transform. And then I think I just want to say thanks to everybody for participating. I'm always very careful to use that word participating. And I think if there's one way to sort of explain to someone what Transform is about, it's about contribution and participation. It's not about presenting and audience and you know, just sort of attending. I'll try to be very careful not to talk about attendees at the events that we do, because, you know, to get involved in our events, you show up and you jump in and you take part in the Slack, in the unsessions with each other, in conversation, and in the hackathon. And those, I think, are really important principles. So thanks for being game, I guess, for that, and not just wanting to kind of sit in a darkened room watching YouTube videos about digital subsurface. And I also just want to call out that I'm sorry, I don't know how many off the top of my head, but many, dozens at least, of people made donations to the Software Underground, to the new society, the newly formed society. Thank you very much for doing that. You know, the idea is to try and make this thing sustainable so that we can organize events and things in the future. So this was a sort of pay what you can or pay what you want event. So thank you for that contribution as well. All the other contributors have been amazing. The instructors in the tutorials, everyone who gave the lightning talk. people who, especially the sort of, I don't want to say leaders, but coordinators, if you like, proposers, champions of the hackathon projects, I thank you for that extra effort. I mean, not an insubstantial amount of effort either, especially, you know, those of you that put together a tutorial, especially for this, like a 3-hour tutorial is quite a big chunk. And here you are just being awesome, giving it away for free with all the, you know, GitHub code and everything. Like, it's incredible, but it's also the engine of innovation. And hopefully, if you're the maintainer of something that someone's just sort of shown back at you in a lightning talk, I hope that was a good feeling. I'm sure you're used now, many of you, to seeing your technology applied elsewhere, but you don't always get to see or hear about it. So yeah, anyway, thanks for being awesome. And last one, I just want to say thank you to the rest of the people involved in the organizing of this thing. So including Dan. I'm looking down at you, Dan, at the bottom of the screen there, with an amusingly placed waterfall. If your hair was soaking wet, it would actually be quite funny. And Rob Leckenby, who's helped us out with a lot of the streaming, the morning streaming. Brendon, who's also been doing the streaming and has been involved in brainstorming this from the start, because this was part of this week was originally going to be a hackathon at his office, at his workplace, so he was involved right from the get-go. Filippo Braghini in Zurich, thank you very much to him for everything, especially all the hackathon focus he's had. And last but far from least, Victoria Lou Devez, who's been helping us from a sort of, I mean, basically, just not to say that we're disorganized or anything at all like that, but basically helping us be a bit more grown up about the whole thing and try to remember to actually do things as we've worked towards this over the last several weeks. I didn't mean for that to be a monologue, but I realized when Dan asked me to come on and say some things that I didn't want to forget stuff. So I've basically just given you a monologue, a soliloquy. Brendon, did you want to say anything that I missed?
Hey everyone. No, Matt, I think you said it well. I want to thank you for you know, for your vision and help putting this together. I mean, I think you know, everyone's been talking about when they joined Swung. I think if you went back into the logs, you find that you might be the first. So you know, from all of us, we really appreciate all you've done, and you know, creating this thing. This is different than other stuff that's out there. Like, we've talked about Swung being a new professional society, and I'm not eager to go online and join in a chat with AAPG members and see what they've been up to, and you know, what their latest things are and what their latest thoughts are on stuff. And so this is more than just that. And you know, after having seen those lightning talks and had the conversations we've had over the past week, I'm really excited about where we're going with this. So thanks.
100%. Yeah, so it's not over. There's one more tutorial. There's the sort of graveyard tutorial that Brendon and I are doing later on basically it's like a primer on web development and getting your tools out there into other people's hands via the internet with Dash and Flask. So if that's something you've always been curious about, come and join us for that. It's a sort of beginner to intermediate, I would say, not total beginner, certainly not advanced in any way, mostly live coding. So that's going to be fun, starting in a couple of hours. And then it's hackathon all weekend go check out the times in the channel, because I forget exactly what Filippo said, and I'm so confused anyway about time zones. But on Sunday, there will be a bunch of essentially lightning talks about the hackathon projects, right? So I think they're 4-minute demos, presentations about what the hackers have been up to. Yeah, so I mean, it'd be wonderful if you could be there. I realize it's on Sunday, but if you're around, do drop in, even if it's just to say hi in the Slack. It's always nice to see the buzz around it for the folks who've been hacking. And yeah, that'll be it until next time. So I'll hand back over to Dan so he can close out in case there's anything else he needs to say. But other than that, thanks a lot, everyone.
Just I guess the Transform Cafe is still open. There's one room if you want to hang out with people, have a virtual beer or whatever. Yeah, I posted this in the Lightning Talk channel, so I'll just say it again here. But thanks to all our speakers, one, volunteering, two, turning up on time with everything ready and free, putting up with my banter in linking the segments. This has been great. I'd like to do it again more regularly. I'll be floating around the hackathon, and if people have feedbacks or want to book me for any parties or any events that need emceeing, I am currently available. But no, thanks, Matt. You know, I'm always happy to help out, do whatever. And yeah, just take it forward, really. It's really your transform. Do what you want with it and have a great weekend and have a great time you spend on the Software Underground. I'm off to have a well-earned beer because it's now after 5 o'clock where I am. So I'm going to leave you all and wish you good luck and good evening.
Bye.